We've really come to the final part now, which is the RBC Distinguished Lecture for 2018, and I'm very happy to introduce to you my fellow countryman, Mark van Loosdrecht. He was a co-chair in our international conference last year here in Waterloo. We're very, very grateful that he came here. He rolled out of the plane last night coming out of Tokyo, just like some of the other external advisory board members. So he really made an effort to be here. We're very, very grateful that you're here to give this lecture. We're also very grateful that you agreed to be part of our external advisory board. I'm going to talk a little bit about Mark's background. I hope you have a little bit of patience with me because it's really a long list of things. Mark really is a water innovator already for a very long time. So I'm just going to go through the list of his achievements. He is a professor in environmental biotechnology at Delft University of Technology in the Netherlands. He obtained his PhD degree and his master's degree from Wageningen Agricultural University, also in the Netherlands, and he was appointed at Delft in 1988, and it took him only 10 years then to become a full professor in Delft. His research focuses on the scientific understanding of complex systems and the development of new innovative processes. And he's been very successful at that. He's interested particularly in new processes related to wastewater treatment and resource recovery. His research has resulted in several new processes currently applied on full scale in wastewater treatment plants, such as the so-called BCFS process to optimize the activity of denitrifying and pee-removing bacteria in wastewater treatment plants. Some other acronyms will follow in a second. The Sharon process, the single reactor system for high activity ammonium removal over nitrate in sewage treatment, and the Nerida process, a wastewater treatment technology that purifies water using the unique features of aerobic granular biomass. Mark van Loosdrecht is editor-in-chief of the IWA Elsevier journal Water Research with a huge impact factor. Mark is member of the Royal Dutch Academy of Arts and Sciences, the Dutch Academy of Engineering, and the US National Academy of Engineering. He was awarded a knighthood in the Order of the Dutch Lion in 2011. And he's the recipient of many awards for his work, both in his own country and internationally. In 2014, he received the Spinoza Prize, which is the highest award in Dutch science. And in 2012, he was awarded the Singapore Lee Kuan Yew Water Prize. And this year, he won the Stockholm Water Prize. He received honorary doctorates from ETH Zurich in Switzerland and Ghent University in Belgium. He's an honorary professor at the University of Queensland in Australia, the Harbin Institute of Technology in China, and the Zhejiang University of Technology, also in China. He has published over 700 papers. He has 15 patents, and he has supervised over 50 PhD students. According to Google Scholar, Mark has over 72,000 citations and the highest age index of a person that I have ever met in person of 137. As I mentioned, we are truly honored to have Mark here with us today to deliver the RBC Distinguished Lecture and to have him in the Water Institute Advisory Board. Please join me in welcoming Mark to the stage.
Thank you. Thank you. Thank you for the invitation to be here on my way back to the Netherlands. It's a pleasure to share with you some ideas about mainly wastewater treatment in this broad context of people, but I will try to address a few issues there where I think it should go. The title is a bit long, and that will also be my presentation. Will not be long, but will be a bit sketchy around what's innovation, resource recovery, maybe a bit blue economy, but that's a bit outside my scope sometimes. So I will briefly go into why do we need resource, why I think we do need resource recovery from wastewater in relation to wastewater treatment plant, a little bit about innovation and how to use that really, and pointing a bit to concepts and misconceptions, discuss a little bit some special recovery options, and then some final remarks. So if you look to wastewater treatment in general, wastewater treatment is not a technical problem. It's really, in principle, a very simple process. So sometimes it's told that wastewater treatment cannot be implemented because it's too complex, etc. If there is complexity, it's the complexity related to the management of the systems, it's long-term investments, usually in the Netherlands, investments of 15 to 20 years, which means also long-term policy and stability for the economic situation to do cost recovery at the public. And that's a much more complicated issue than aeration and mixing and pumping. That means that in weak government systems, there's usually the problem for implementing wastewater treatment. One of the options which is proposed, which I think is an idea at least to work on excessively, because it's not a problem to implement very often, to find financing from, for instance, World Bank, etc., to do the investment in the treatment plant, but then it's often a problem to pay for the salaries of the operators, etc. And it might be a good idea to figure out ways to get enough revenues from the operation of treatment plants to at least make sure that the operation and management of a treatment plant can be paid for, such that the operators have their own salary in their own hand and their own operation. Resources to recover are water, energy and materials. I'm mainly focusing on materials, but I will make some remarks on the others. Now, looking to this kind of concepts, I looked a bit around and looked what broad instances state about this, and also give my opinion around it. This is what you usually see. This is an infographic from the World Bank, which I put in two to keep it visible on the screen, showing how we could get the waste out of the water, or waste to resource concepts. And it's often divided into 2 or 3 parts. That's of course a treated water. It is a very important, that's the most important resource we cover from wastewater. The sludge, and then very often phosphorus is meant, and that's then worked out. And what the problems you have here is that treated water, to get value out of that depends of course very much on local situations, what is possible or not. And for many of the applications like irrigation, like recreational use, it's very difficult to do cost recovery. If you produce water and you send it to industry, there might be options to do that, but even there the problem is that very often the industry would require much higher quality than what you get from a normal effluent. So you would also have to invest in bringing it to the quality to the industry. Sludge, energy generation, biogas is often advertised as a good way to get maybe even CO2 credits. My take on that is that in most of the cases, if you really want to advertise this as a climate-friendly approach, virtually every treatment plant which makes biogas leaks biogas in the order to 5 to 10% of the total methane produced, meaning effectively there's a very big negative impact on the climate from virtually every biogas installation, and that's including all the ones in the Netherlands and in Germany and high developed places. It can be overcome, but it's not easy. Biosolids, we know the discussion, it's not easy to make money out of that. You might be lucky if you can get it on the land, and otherwise it costs you money at the current ways. And the phosphorus, I will come back later in my talk. Other example from, in this case, a market, Veolia, who also is looking to this kind of concepts. And again, more or less the same teams. And that shows that it's thought about, there are going on, but as I already remarked, most of these concepts, they will have problems. We'll come back. And the problems in getting an economic resource recovery, because I approach this very much from the fact that it should finance itself and not due to other things, is that many of the concepts are just relying on the fact that it's a good idea. That means it needs subsidy in order to come there. Now, I'm not against adding subsidy in things which society wants. I think that's a good idea even. But I think in the conceptual design stage, etc., it would work much better if you start from a point of view to do it really cost neutral. Because if you are managing to do that, you will also manage to get it introduced much more quickly than when you rely on it. Moreover, you make the cost not very visible. There's often no attention for upscaling potential, so it's nice to do something on a small scale, but how do you do it now on a large scale? And that's where a bottleneck of many of the resource recoveries is. I will come back to that. Value chain business models are not there. Systematic analysis of options is often not there. People jump on a resource recovery option because they hear about it and they don't systematically analyze what's possible. There needs to be better interaction between engineers, economists, maybe psychologists, social economists at least, to see what's going on, but that interaction hardly exists. And regulators are, in my view, too often used as scapegoat for the fact that your innovation doesn't work. It's usually the 5 points above, which are the really one which is missed, and then the regulator will not respond to that kind of changes. 2 points from that recovery thinking which I observe is that a lot of people in the resource recovery field, they think like a farmer who has milk or who has sugar beets and complains that he doesn't get the amount of money for his product what you have to pay for if you go to the shelf of the supermarket. And that's just neglecting the whole supply chain in between, which needs to be financed in some ways. And if you make initially economic evaluations for resource recovery, putting in the final product price, of course that looks very positive, and then later on you find out that the market is conservative or they don't want you to pay the value you think it has. But be aware there's a lot of points there, and that has to be taken much more better into account, finding out what the price is of a raw resource instead of using the final product. The other main problem which has to be addressed, and that's partly this upscaling aspect and partly also how to start to organize it, is that there's a lot of attention to, for instance, recover phosphate, but not attention to how then integrate this into the value chain in the market for phosphate as a whole. We look a lot at water products, but the main problem is that industry is used to one big supplier. At least most of the chemical and fertilizer industry is used to have one big supplier. They make a product out of it and they send it to the consumers. It's almost all within a private market. If you go from wastewater, we end up in a very different situations because we don't have one supplier. We have in the Netherlands already 300 suppliers. Here in Canada, even way more. And that's not only a very distributed supply system, but also a public instance. At least the sewering is usually public, and very often the treatment plant also, or even if it will be private, and that private company starts to make something out of the public good wastewater, and it's profitable, immediately we will get problems around public-private relationships. So these two things will have to be addressed in order to really make it work, that we go from, say, waste treatment facilities to really production units. There's distributed production as well as this going, what is the value of a raw resource you recover out of wastewater, and how is that value rightly distributed about the different partners in the value chain. If that's not part of your thinking, if you design a new wastewater recovery option, you might design your option in a wrong way. Now, demand-driven resource recovery is not new. It existed already a long time ago. This is an example of a company which functioned in Europe. Granular has been functioning for about 20, 30 years, fully commercially, with rather complicated technology to recover nutrients in cities and sell this to agriculture. And another example is Prague. There's a factory which is still standing there as a kind of industrial monument, was recovering phosphate from the wastewater for Prague before the rest was discharged in the river. Nowadays, instead of it, there's a wastewater treatment plant behind it. But also this was a commercial activity, and both, of course, went out of operation by the time that Haber-Bosch process and oil became there. The Haber-Bosch process leading to very cheap ammonia and oil as an energy source to much easier transport and mine phosphate from all kind of faraway places. So aim should be to develop systems that are self-organizing due to an economic driver, in my view, of course fitting a modern society. And the only place in modern society where still this is more or less working is in the metals industry, where scrap metal is quite efficiently collected in Western worlds by a kind of private system where it works. And it's also I think that if we as engineers would be possible to generate products which have a high value, that somehow market will organize itself. If we will make products which are low value or which need subsidy, we all the time have to wait for governments, regulations and other things to happen. Also, resource recovery is not entirely new from the point of view that it already happens. In quite a lot of places in the Netherlands, resource recovery is implemented to optimize the systems. This is a treatment plant in the Netherlands, Olbergen. It's a municipal wastewater treatment plant where also quite a big fraction of the wastewater comes from a potato industry. And the water board decided to keep that potato industry wastewater a bit separate from the municipal treatment plant, but integratedly treated at the same site. And its recovery effectively sulfur from the biogas, which is there. It of course recovers the biogas, makes electricity and heat out of it, and it recovers some phosphate as Struvite. It recovers the sulfur to prevent corrosion problems in the biogas installation, in a burning installation, and it recovers the phosphate to prevent maintenance problems later on in the installation. Other example is sludge removal, actually in my view one of the better sludge treatment facilities. It uses bio-drying. It takes sludge and it uses just metabolic heat generating from composting just to dry it. Generates a lot of heat which is used for district heating. It generates a lot of ammonia in the off-gas of the composting plant, which is recovered as ammonium sulfate and brought directly back into the fertilizer industry. And the dried sludge is sent to an electrical power plant where it can be directly used for energy generation in power plant. Whether that last one is the best option, we can discuss, but in this way a lot of resources are efficiently recovered. Now, if you want to do resource recovery, we need innovation. So some thoughts about innovation. One thing, certainly from an academic perspective, what is needed here is curiosity-driven research. We should not only see, okay, we can recover phosphate as Struvite, let's make a Struvite recovery unit. We need research to investigate what's going on with phosphate. How can we find ways to alternatively remove it and not jump for the best first solution, but take time to analyze what's going on and based on that slowly discover maybe new options for recovery potential. That curiosity knowledge cycle is something which typically happens inside academia, and that will only lead in the end to innovation if there's a good interaction between academia and utilities and industry. Academia should not start to behave as utilities or industry. They have their own role. That's this curiosity-driven knowledge generation. But knowing what the problems are, and you see some observation, you can also solve problems in the end. And that together leads to potential for innovation. As an example, I use always here a project from our own laboratory. One of our researchers is Dimitri Surikon, is very interested in what do bacteria do in the soda lakes in Siberia. This is saturated soda, which we normally use to disinfect wounds. There's a lot of microbes growing there. If you then know that there's H2S in biogas, you might want to use this alkaline bacteria to remove the H2S, because in alkaline solution H2S is way better soluble than in neutral solutions. That's possible, but there's not really a big market for H2S removal from biogas. There's even a bigger market by removing the H2S on the gas fields here in Canada. And so in the end, the technology is used on the gas fields in Canada to clean up the natural gas and produce elemental sulfur, which until now not has a big value because there's quite a lot of elemental sulfur around. Now, if you talk about innovation, that's not a linear model as it's sometimes thought. Someone gets an idea and you slowly scale this up. If you do it well, it's a kind of circular process where all partners in that circular process communicate to each other or have interaction at least. And that's the technical science, the hard sciences you could say, that's the soft sciences. That's the product engineering, the product development, and that's also then the services part of products. And that interaction is needed, and sometimes that interaction is not occurring in the right way. And then you get that innovations or inventions, I should say, stall and never lead it to the market, or only very difficultly lead it to the market. Examples are if there's not enough combination between science knowledge and business needs. People within the university are very enthusiastic, working on things, university and often technology development institutes, but there's not really a business needs. A lot of the energy and resource recovery at the moment falls in this field. Decentralized systems, a lot of them falls in this field. Not all, I think, what Aerobic is doing, not because Tove is here, but they try at least to do it in a much more coherent way than what you see in most of the cases around decentralized systems, and a few more of these approaches. It's nice technology development, but without any attention how it will be picked up by the market in economic or social sense. That leads to stalling of technology development. This decentralized treatment, I use that always as example, because a lot of the projects and things, they are hampered by the fact that if you would start to analyze them, they in the end require more energy, more money than a big centralized system where you can depreciate everything in 20 years or 15 to 20 years. And this development stalls for that reason. There's not really a strong enough system advantage, except that people might like to have a decentralized system, and it sounds nice, certainly in many of the project planners and town governments. Example which works the other way around, I don't have time to go into details, is a pharma filter. That's a decentralized system for hospital treatment, which nicely captures all the pathogens and all the micropollutants from that particular hospital. This has not been developed to treat the wastewater of the hospital. This was simply a logistics manager within the hospital who wanted to optimize the overall logistics within the hospital. Then discovered that if he was doing so, the way he would discharge the wastewater would not be acceptable for the town. So he had to implement their own wastewater treatment system, which then led to further optimization, because heat from the wastewater and also the water could also be reused in the hospital. But it was not starting as a wastewater treatment. It came out of economic optimization of the procedures within the hospital. And that is now implemented in several places in the Netherlands. Other area which often occurs is there's very much attention for technical capabilities, usually between industry and universities. And again, not so much attention, or not enough attention, but there's really a societal need for the development. Two, which I mention usually, is the phosphate recovery aspect and the membrane bioreactor. The phosphate, I might come back, but the membrane bioreactor, I use an example. It's a typically technological push development. There are very good applications, by the way, for membrane bioreactors. I talk here in the context of municipal wastewater, where you see that there has been a lot of hype in the early 2000s, leading to implementations about 5 to 10 years later. And then it stalled, and that's even in 2011 or 12 was the extrapolation was as if it would keep growing by market reports. But if you now look to MBR implementations over the time, you see that after the, say, peak around 2010-12, it's falling away, and that's simply because the technology has advantages, but the potentially better effluent quality can also be reached by more simple technology like sand filtration or tertiary media filtration. It costs more energy than the normal wastewater treatment plant. It costs more chemicals than a normal wastewater treatment plant. It costs more investments than a normal wastewater treatment plant. And the advantages are simply not big enough. There are examples in industry and others where it is the case. We can discuss about that. As Roy already said, we developed a new technology. I'm not sure whether we whether you should call this a really ongoing innovation, but I want to use this as an example how we relatively quickly went through it. Again, no details. But it's an example of one of the implementations. So the technology is based that we have initially investigated how do our microorganisms develop into certain morphologies, preferentially a granular morphology, simply because if the granule has an advantage in the treatment technology that it is much easier to separate from water than flux. And if you're able to do so, which was known for the anaerobic wastewater treatment, you are also able to make more compact installations. This is an example of one of the first bigger implementations in the Netherlands, in the north of the Netherlands. See the treatment plant. Let's see, yes, this works. This is the granular sludge plant, which has the commercial name Nereda. This is the old-fashioned treatment plant. Both treat roughly 50% of the wastewater. And you can appreciate the much smaller size. These tanks are 40 meters and these are almost 50 meters in diameter. The much smaller size, but also the much simpler, effectively, installation. And the effluent quality from this plant is even better than from the main plant. Combined with about, and this depends a bit on the situation where you are, 20 to 30% less energy consumption, of course a much lower land use, a lower investment cost. So at least there are a few factors on the economic side which will help to push the technology. And as one of the persons in the room, I forgot the name, from Brazil just said, the fact that it requires much less land area is a reason to choose it. And then even if the government does not apply strict nutrient standards, you get them more or less for free. So there's an advantage on it to build this kind of installations and in the same time get nutrient removal without a government there. The first full-scale installation was in operation in 2012, full operation. And currently this treatment plant in Ireland, in Ringsend, is reconfigured into the Laureate technology. This first tank here that is reconfigured, the rest has to be changed, is under change at the moment. If this is implemented, that would mean that in about 5 years after the first introduction of this technology, also the largest treatment plant, or one of the largest treatment plants in Europe is now reconfigured in it, which means that more or less it's completely market ready. Innovation always takes time. Bringing new things takes time, and that's partly because you need the time first for the more curiosity-driven research, which took probably 10 years to really understand, in this case, what makes morphology. At that time, we were not busy trying to design any treatment plant. We were just interested what makes morphology. Is this the bacterium? Are there other factors? And what's going on? Then you need time to do a pilot plant because nobody will invest without showing it and getting all the procedures done. And doing the design, construction, etc., etc. These are not installations you build overnight. So that took about, that time was also again 10 years to get from the lab ID to the first full-scale reactor, which is, I think in wastewater terms, quite quick. But for electronics, that's still maybe slow. So currently there are about 50 plants in about 5 years. And in quite a different continents, effectively every continent, even North America is now the first plant in getting in operation. And success factors were here that essentially technology is relatively simple if you understand the interaction between biology and process technology. That's the complicating part here, but mechanically it's way more simple than conventional treatment plants. It helped that we have, the speed helped a little bit that we have dedicated organizations in the Netherlands for water. That's the water boards. So we're not too much in a political organization where we have to do the innovation. We are more in engineering surroundings. We patented the system. This was crucial for the development. Not for the implementation in practice, by the way. It was crucial for the development. We were able to set up a national research program which lasted 10 years. No-go or no-go decisions implemented in this 10 years. research line, we said we go and work on this, and it will take 10 years, and we will get there. Moreover, we only, after 8 years, someone came to us and said, well, you have a public-private partnership. Now, we had never been thinking about what kind of organization we would need to get this, or in what kind of terms this could fit. We were just trying to see the best way to bring an idea to the market, and that's probably also contributing to the fact that we were relatively successful. And of course, there needs someone who really pushed the car, and that was in this case Helle van der Roest. So this at least is more or less how it should be, because indeed the university with the ideas, industry, the HV who could bring it to the market, and the users and the government were involved in this development program. Now, looking to resource recovery, there's a lot of activities on different places, I think especially also in the Netherlands again. Here a list of potential recoverable items from a treatment plant. I listed them maybe a bit on order of what would be most important to do. Water is evident. Nutrient recovery, fibers, heat, energy. The italic ones are all full-scale examples in the Netherlands. The two which are underlined are currently demo plants in the Netherlands. So you see there's a lot of potential for resource recovery, different items to recover. And I will treat only a few of them. If you're interested, you can go to this website, EFGF, where most of the details of all the different recovery projects can be found in the Netherlands. And these are maps showing the installations which do energy production at the site, which recover fibers, mainly cellulose, at their site, and which recover phosphate. That are the main ones. If I look to the driving factor for this whole process, is very much technology push. The water boards have said, we will go for resource recovery. We go there and they try to implement as much as possible. There's also a policy push from the national government, because the national government advertises and pushes for circular economy, so also this fits within it, and of course the climate measures fits within. So there's a very much technology and policy push. There's not really a market pull in this whole process of all these installations. And it's mainly following existing opportunities. It's not doing an analysis of what is there and what can we do best, but there's a technology, oh, let's try it and see how far we reach. That's, by the way, not by definition wrong. It sounds maybe the way I tell it, but there's no problem being opportunity driven, etc. But sometimes also good if you do a system analysis and see what's actually potential. And as I said, there's no, for all these things, there's no resource demand for what is recovered until now. Success of the current recovery projects is, from resource recovery, maybe limited, but many of these projects, they are very successful because on one hand, they very often lead to cost savings at the treatment plant. As I mentioned before, it's not by definition that if you recover resources that it needs cost. There are also cost-saving items in it. And of course, there's a very positive communication with the public around all these projects, which is also good for an organization like a water board. Going to a few of these projects, energy recovery, it's very often advertised that water resources, wastewater plants should be energy producing. In my view, wastewater plants should be energy autarkic, should be energy neutral. Because from a wastewater point of view, it's much more efficient to have no cable at all, certainly no electricity cable coming to the treatment plant, being able to generate your own energy to treat your own wastewater which you receive. It's maybe not so relevant in Western Europe, but in a lot of places, electricity supply is one of the limiting factors for stable operation of the treatment plant. So being able to do that at site saves you costs, because you do not need to pay for the cable to your treatment plant, and it makes it also more reliable. A lot of the energy producing plants which are advertised, they effectively import energy in the form of food waste. You can say that's food waste, but essentially you import energy, and you cannot call this energy producing if you first import energy and then export only a part of that energy again as biogas. That's just converting a low-grade energy to a bit higher-grade energy. What is forgotten here is that in the water cycle, there's 10 times more energy going into the heating and the heat value of the water than in the organic carbon which is there. And you could quite easily recover heat, either to heat or for district cooling from certainly the effluent of a treatment plant, which is rather clean. And there are now also good examples where this works very well. And somehow overseen, that might be from an academic perspective, because it's much more interesting to look to digestion and biogas formation than just a simple heat pump or heat exchanger. But from a resource recovery, this is a much more interesting one. Energy is not an economic driver simply because energy is very cheap. It's a climate impact driver, which could be very important. And as I said, the heating might be a factor of that. But the cost is always almost always much higher because you have a very small scale system. Other interesting one which popped up when someone suddenly realized that there's a lot of cellulose in wastewater. We all use toilet paper. In Europe it's around 10 to 12 kilograms per year. Here in North America it's even more. And it's usually thrown into the toilet, at least in our part of the world. Ends up a treatment plant, and it's a very significant fraction of the wastewater COD. That's why it's a bit remarkable that in all the COD influent characterization, on all the characterization which is done in the past, is 10 to 15, maybe 20% of the incoming COD has never been recognized as a single separate component. But it's easy to recover. The sieving methods are already there. You can very easily recover it. And because certainly at the low temperature, but also at medium temperature of 20 degrees, cellulose is at 10 degrees hardly degradable, and at 20 degrees moderately degradable. It doesn't contribute much to the nitrogen removal. Sieving it out up front will mean that you get a much more activated sludge, meaning you can have a much higher load to the treatment plant, and in that way, using a sieve, you can very much increase the loading to the treatment plant without expanding too much without expanding the plant or doing investments. So that's why sieving is implemented. It minimizes it might optimize treatment plant. Moreover, your sludge at lower temperatures will contain high fraction of non-degraded cellulose. If you sieve it out, that cellulose can be easier either burned or sent to another way than treated as waste sludge. It's easy to recover, it improves plant optimization, it's more or less cost neutral, there's no real economic value. There is a value, for instance, you can use it in asphalt making, and then you get nice attention from the press. Then they say, bicycle roads made out of toilet paper. It's a small part because it modifies the viscosity of the asphalt. And of course, it's better to use toilet paper there than a tree which you cut for it. But the problem is that the logistics of bringing the cellulose from the treatment plants, bring it all together to make this an economic operation is very complicated. And the amount of cellulose, it sounds a lot, 12 kilograms per person per year, but think how much paper you use in total, and you know that it's a small fraction of the total cellulose conversion. Phosphate recovery is also very often advertised, and here, this is a diagram of phosphate flows in the European Union, and you see that effectively only 3% of all the phosphate flows, or a small fraction of the total phosphorus, is coming from humans. There's a big cycles in agriculture and other places, and that means that if we recover phosphate from the wastewater, that's not something we should not do. We should do it. But we have a very small impact on the global cycling of phosphate in the economy. And then we will not be seen as a dominant player in the discussions around phosphate. There's of course much more to do with animal manure, in better fertilization at agricultural feeds, places, etc. So this is the first limit why phosphate recovery doesn't push through in significant manners despite all technology development. The main part everybody focuses on is Struvite. The problem with Struvite recovery at wastewater treatment plants is that you can recover maybe 10 maximum 15% of all the phosphate entering a treatment plant as Struvite. The rest ends up in the sludge and at other places, and you don't recover it as such. It is, however, a very nice way because it's implemented quite often, like here in Amsterdam, because recovering the Struvite improves sludge dewatering, saves a lot of sludge handling cost, might save maintenance cost, and a few other aspects. And it's a nice way to communicate with people, making them aware what urine is, where it goes, what you can make out of it, and you can deliver it potentially back to the public as is done in Amsterdam. But these are very nice public actions. There needs to be a much better integration because, again, the amount of phosphate recovery here is small and where it goes is small. Moreover, if you start looking where phosphate goes, every treatment plant has certainly iron in the influent, and certainly there where there's groundwater infiltration into the sewer system, like in the Netherlands, there's also iron infiltration in the sewer system. It's a bit an unknown source of iron. All iron entering the treatment plant will end up either as iron sulfide or as vivianite. And vivianite is a reduced iron phosphate compound. And somehow this is a kind of blind spot in the research of, you might think that iron and phosphate removal by iron is very well known, already a century old, but nobody has ever looked what is the speciation of iron into the treatment plant and seen that even in aerobic compartments, if iron is bound as vivianite, it will remain a reduced iron compound. It's a major phosphate source, phosphate mineral in the digested sludge. It has a nice blue color. And we found out that you can even recover it quite easily with machines. Now, I'm not saying that we should produce vivianite, but it's a different option which you get if you're curiosity driven in your research and look what's going on instead of only goal oriented in your research. Well, I forgot that, I didn't have that slide here, but iron phosphate, if you want to buy it on the market, is more expensive than Struvite. You think it's lower value, but essentially it's more expensive. And also vivianite is more expensive than Struvite per unit of phosphate. So also from a market perspective, it might be of interest to look to that. If you in the end want to recover all phosphate, the only way is to burn the sludge, or if you are not allowed for land application, by the way, to burn the sludge, because that's the only place where you can recover all phosphate, and that's currently installed in the phosphate in the sludge burning facilities in the Netherlands. The reason here is not directly that, again, that phosphate is important as a resource, but is simply cost of dumping of the ashes saves about 70 euro per ton of phosphate recovered, and you get about 10 euro per ton of phosphate recovered. So it's clearly driven by legislation in the end, because dumping cost is depending on government regulation and taxes. But it stimulates, in this case, the recovery. And where it goes, I don't know, but from my point of view, I always say that if phosphate in 20, 40, 50 years is really a strategic issue, it is a strategic issue, it might be better to, for the time being, pile it up somewhere until it becomes a strategic need and see it as a national resource. These are materials you can recover. Now, currently we look a lot to materials we can produce in the treatment plant. And there we look mainly to polymers, polymers inside organisms called polyhydroxyalkanoates. Essentially these compounds which are fat reserves for bacteria. They don't make the same lipids as fat storage as we do. They make this kind of chemicals. They're polyesters, and they are very much similar to polyethylene, polypropylene in their properties. Interesting thing is that virtually every bacteria can make it, so all the bacteria in a wastewater treatment plant can make these compounds, and you could, instead of trying to maximize the amount of sludge, trying to maximize the amount of PHA inside the biomass. The nice thing of these bioplastics is, of course, these bioplastics are biodegradable. Not all bioplastics are biodegradable, but these are. And they can be used for many different applications, not only as a biodegradable plastic, but potentially in paper additive, as feed in aquaculture. The monomer can be used for organic chemical synthesis. And if you methylate the monomer, you have a better addition to fuels than ethanol. So the advantage would be that from organic waste we could make all kinds of different products. There is one large pilot plant, demo plant going on in the Netherlands, the so-called PHARIO project. It's a program from previously Anox Kaltnes, but still Anox Kaltnes collaborators and the Dutch water boards. And to see if we can maximize the PHA content in activated sludge. That's possible. That's even consistently possible on all kinds of activated sludge plants. That's technically it's not a problem. It's scalable. We can do this everywhere, and potential for the Netherlands will be around 25,000 tons and Europe 500,000 tons. This is, by the way, still small in plastic industry terms, but it's significant amounts which could realistically be produced. As shown here, we can go up roughly to about 50% of the sludge being this plastic. So it's a significant amount in the sludge which we can produce. What's the problem here? Extracting the PHA from the biomass is also the limit for the pure culture production of this process. The cost versus the market price are not really balancing. And what is missing, essentially, it's nice to have biodegradable plastic, but there are more other biodegradable plastics, especially polylactate, and there's not really a unique selling point for PHA over other compounds which would make it feasible. If that's there, if we would find with material scientists that point, then this would go immediately into, I think, into further development. Currently, we're still trying to struggle to find that unique application. The other polymer we look at is the exopolymers. Again, this was more initially curiosity-driven research, because if you look into EPS, a lot of people talk about EPS in fouling layers and membranes, etc. Hardly anyone does any analysis on it. Methods which are used, they are unclear extraction methods, unreliable methods. I have no time to go into the details here, but mostly you do not extract the polymers, mostly you do not analyze the polymers. You get some data which is good for publication. Often I think they should not be good, but it is until now. The problem with polysaccharides is its versatility. DNA is a very simple molecule. We have a lot of fuss about our DNA analysis. It's essentially just 4 different beads on one and the same string, coupled in the same way. Proteins is already a step more difficult, because then we have 22 different beads, still more or less on one string, but with more complicated tertiary structure to elucidate. Polysaccharides has at least 50 different monomers, which can all even be derivatized with all kinds of side groups, and a lot of different way of bonding them together. So the order of magnitude to analyze a polysaccharide is at least a few orders of magnitude more complex than DNA. That's of course also the reason why it stalls, but that should not withhold this. And this is an example of aerobic, of nitrifying granular sludge. The EPS in there are glycosylated aminoglycans, proteins. None of the current used extraction methods extract this kind of compounds. None of the measurement techniques will detect that these are glycosylated proteins. But they are the dominant factor, and they're about 30% of the mass. Now, we got interested in it because we understood how we can design process to convince bacteria to make granules, but we did not understand how bacteria make granules, so we started to look in it, and we found there polymers which are like alginate. That's why we call them alginate-like polymers. They just embed the bacteria in the matrix, and all these fibrils, that is not due to drying, they are really fibrils, inside the beads are binding the bacteria in a gel matrix, like here in a gelatin pudding. That polymer is quite different from flocculant sludge, because if you make gel beads out of it, or look to the strength of the gel, if you extract the EPS from BioP flocculant sludge or from BioP granular sludge, that gel is way more strong from the granular sludge, and that's interesting. That's an interesting property from a market perspective. Because gelling compounds cannot be based, they are not made out of oil-derived polymers. That's purely coming from natural sources. And that gives an opportunity, because now we might recover something which has market impact. We looked compared to the alginate market, because more or less the functionality is the same as alginate, although the chemistry is different, the functionality is the same, similar. We can get significant amounts of this alginate-like material. If you look, the wastewater treatment plant of Utrecht, a moderate treatment plant, could produce 2,000 tons per year. Total production of alginate is 36,000 tons per year in the world. So if we start producing on even one treatment plant, we could already supply 5% of the market. So we become an important player. 2 years ago, we had 20 existing Narada plants, or 1.5 years ago. That would mean that at that time, if you would extract all the polymers from these plants, we would have the same amount of material as the total world alginate market. So we could recover something with market impact and not just a small volume contributing. Now in the meantime, well, the functionality is the same. In the meantime, we know the composition is different. But there is currently an extraction facility under construction. We'll start operating next year of about 500 tons of this polymer per year. And there is a commercial client buying this for the coming years from the water board. So the first parts in the value chain are there. The commercial client does not yet know which product he is going to make. But it's important to see that there's at least direct commercial interest. For the water board, it means sludge reduction, it means contributing to circular economy, and it's more or less cost neutral for the water board. We have seen in the meantime that we can make a lot of interesting materials out of it. We can make materials which look like the shells of shrimps and crabs, which has not been possible yet with oil-based chemicals. So these nacre-like materials, this is the same structure as you can see on the electron microscope as from a shell, giving also then the material properties of the shell of a shrimp or a crab. Moreover, this material turns out to be flame retardant, and we can treat it as any other plastic. We can spin fibers, we can make coatings, we can mold it. Which is main important is flame retardant. So we have a plastic which doesn't need bromated compounds and other things to have it flame retardant, which is probably the most unique selling point we have at the moment. This is just showing that up to 1,000 degrees it doesn't flame, and we can put burners on it. It might get a bit red, but it's not burning. There's a range of other applications we have figured out in the meantime. So one of the first ones we're now looking at is using it as in agriculture, because it's a much quicker entrance where it has nice impact on the seed germination. Can make elastic materials out of it with some modifications. This is made right away from the sludge. That's why it's still black. We have one product on the market, Delft Green. It's currently still alginate based because there's not enough material, but the material is having the same thing, which is used as a curing compound in cement, improving the strength of the cement in the end. And with the big advantage, it's water-based instead of solvent-based for the current curing compounds. This is not going to sell a lot, because that would be a few % of the total amount which is produced. Found another nice application. If we mix it with nanocrystals, we get a very nice material, because these earrings are only made from used toilet paper and slime from bacteria. Nice oyster shell-like material, but it has also more or less the strength of glass fiber reinforced polyester, and again water-based. So that it is possible to make all kinds of nice materials. There's a kind of integration of wastewater recovery, because these is made from the PHA I just described. These leaves are made from say used toilet paper and microbial slime. The blue color is derived from the iron phosphate, the vivinite, and the red color from the Anomox bacteria in the sludge. So you can see that you can use a lot of aspects from sludge create something which has a positive feeling and where not directly get a kind of yuck factor because it comes from your toilet in the end. Currently, we are looking here to upscale to with one of the outlets would likely be, yeah, I'm almost finished, produce then this ale-based cellulose composites for car manufacturing as a replacement for fiber-reinforced composites, etc. In the initial production of the material, we probably save something like 2/3 of the total energy cost for production of the materials. The car with the same strengths and capacities would be about 100 kilogram lower. This is for European cars, I should add here. And that would save around 0.7 liter of fuel for every 100 kilometer you drive, or you can drive longer on your batteries if you have an electric car. That's with the composite industry. We're working on that. So we hope in 5 years to have that fully on the market with this set of collaborators, again in a PPP construction. And to conclude, I think we need to develop water treatment systems that are economically self-sufficient, energetically self-sufficient, not producing, but which recover resources to take care of that economic self-sufficiency, that needs good innovation systems, that needs the respect for universities, that you do curiosity-driven research and not only go for the first application, that needs a good integration with economic and market research to understand where the bottlenecks are so that you can solve them instead of hide them to keep your promising solution go well, and good definition of what's limiting the resource development. I think also it's good to recognize if we do resource recovery where we do this simply to have a kind of research going on, whether we do this to optimize the plant or whether you do this because there's a really economic driver for the resource recovery as such. With that, I want to acknowledge, of course, all collaborators of the past and the PhD students, the Dutch Water Boards and the Science Foundation were important there. And want to invite you next year to come to Edinburgh for a whiskey and listen to leading edge technology at the Iowa LET conference. Thank you.
So there's a real strong movement to recovery, especially in the US, and even changing the name of them from wastewater treatment plants to resource recovery plants. But there's a trade-off. I guess the question is there a trade-off for what their primary intention is, which is to protect the environment and public health?
Yeah, so let's be clear. If you do resource recovery, neglecting health, neglecting your effluent quality is doing a very bad business, because that's the prime reason to be there. That's, so these 2 points are important. Well, I think that's your boundary condition within your work, but I don't see that these would not match together. With the PHA, we have a good example because the technology I showed is technology developed by Arno Skalters from the point of view that we treat wastewater and try to make as much PHP within that context. We have followed a different line. We said we have waste and we try to make as much PHB, whatever the effluent quality is. Of course, we can make much more efficient PHA, but in the end, you will have to treat the waste, the remaining water likely, to make it satisfying effluent standards. It's a different design guideline. Both could work to feasible, will and can work to feasible systems, but you have to take that very explicitly into account. Certainly also the health aspect, that you're not hiding a lot of germs inside what you're spreading around and have, in the end, a negative impact.
So Mark, like you, I remain a fan of sludge drying and think that it's still a viable technology for the future. Why is it that you directed those dried products to power production rather than cement production? Because the ash management, you said that recovering nutrients or elements from ash is not economically viable and probably will not be for a while. So in the cement process, the ash can remain in the clinker, right?
Yeah, I think at the moment, the example I showed was from this bio-drying is simply this company has been trying to find a way to get rid of waste activated sludge for minimum cost for the waterboards without investing then in a huge burning facility. And yeah, I think they found a very elegant way of doing that. It's not very much reproduced. For some reasons, I'm not, well, there's a few reasons around that, but I believe it's in principle a very interesting option. In the end, indeed, you burn it, you get then your minerals in the ashes, and currently these ashes are not well, economically, in generally not feasible to recover material out of that. On the other hand, if you put them in depots which are well managed and controlled, you could always, if in the future there is a lack of resources, recover them again. So I think that's more strategic. You can work also strategic. If you foresee a problem in 40 or 50 years, you can already now adapt to it. And that's not a bad option if you at least do this consciously and manage it as such. Yeah, in the end, part of it is it's total optimization, and that's in every country is different. That's why here you don't have much sludge burners compared to the Netherlands also.
Very interesting talk. My question is, what is the catalyst that got industry in the Netherlands to participate in this resource recovery for wastewater?
That's of course very difficult. You could say that's motivation. That's partly true. I think it's motivation by the engineers. They want to improve the system. They want to contribute to sustainability, etc. But if the engineers want it, you also need someone higher up who then lets you spend the time and the resources on it. And that then helps if a government emphasizes a lot of circular economy and this kind of aspects, because that's a point. I think it also helps in the Netherlands that there are water boards, and the water boards have as only task to manage the water. They don't have to build theaters or make roads or other things where money could be spent or where glory could be gained by the people who manage the system. And we have a benchmarking system in the Netherlands. Well, two other things. The water boards have a unified R&D program. There are 20 water boards, but they have together one big research program, so it's not split up too much for the research. And in the benchmarking of the water boards, of these 22 water boards, the research part counts for 25% of the benchmark. So also that helps, of course, because in the end, the higher management wants to score high in their benchmarking, and this is 25%, so if you neglect it, you're anyway low in the benchmark. So that helps.
So, Mark, if theoretically a country in Africa wants to jumpstart their wastewater treatment plan to meet SDG 6, do you have, this may not be a question you can answer, but do you have advice on, is it diversification, is it their footprint? I like the idea of energy neutral for sure. And I think ministries like that too, but do you have advice, or what, do you think it's? Yeah,
so related to Nereda, I think, well, there's a few advantages because there's 20–30% less energy need. There's only a need for an influent pump and a blower. All the mixers, all the return pumps, so a lot of mechanical equipment is not needed. So that saves a lot of import, which is important very often in these countries, because that has to be paid in dollars or something like that and not in the Ghanese currency. So that's important. The real problem is, of course, that this is a centralized facility which only works if you have a good management and you have built up a sewer system over time, and that's not something which you do overnight. A wastewater treatment plant you can build in a year. Sewer system that needs long-term planning, long-term management, and I'm not sure whether that's the best way. I think it's the best solution in the end, but within the governmental context of a lot of these places, I'm not sure whether it's the best solution. At least as far as until now, the need for resources, the cost, etc., they're all lower. And yeah, unfortunately, if you, so I'm not completely sure if you cannot manage that, how to, then you have to invent indeed very much decentralized solutions so that people locally in the local communities are empowered to just invest on their own for their own good environment. And that's another solution. That's not a design parameter which you have to take into account.
I propose we close the session. Let's give Mark one more time a